All right, section 5.1 is all about sequences. Okay, so sequences, obviously the idea of just a pattern, specifically of numbers, given by a rule. If it makes you happy to say formula, that's Q2. Okay, so here's the game. If you can write a formula that looks like this, the nth term is given by some formula, and it'll work for any term, then this is what's referred to as the explicit notation. That's cool. If you can't, if you can only say this is how I get from, I have to denote it as the first one, and then to get to the next one, I do something to, whether it's add or multiply or minus or whatever, the previous term. So the nth term. Some people will write it this way, nth like this. Some people write n minus 1 and call this the next term as tn. And then you can say, like, well, you multiply the previous term by 5, or you divide it by 2, or you add 5 to it, or whatever it happens to be. This is what is referred to as recursive. And of course, this obviously comes into play in Excel and programming frequently. So we'll get into that as we go along. Okay, but just some ideas here. Let's see what happens. So if you had this sequence, 1/3, 4/9, 9/27, 16 81st, 25, 2/43. Where are we at? 36, 7 29ths. Let's think about this for a Jiff. These are our terms. This is the first term, second term, third term, and so on. So my n, this is n equals 1, if you will, n equals 2, n equals 3, and so on and so forth. Let's see if we can find a pattern here. All right, cool. What's going on the bottoms? Well, I feel like this is 3 to the first power, 3 to the second, 3 to the third, 3 to the fourth. It's 3 to the nth power in the denominator. Sweet! Now, the numerator, however, is a little funky, a little different. What's going on there? Well, it's 1, 4, 9, 16. Wait a minute. Isn't that n squared? My God, it is. So your explicit formula is simply n squared over 3 to the nth power. Okay, and then of course later on we'll talk about, hey, what's this thing doing? Well, obviously it goes to n goes to infinity. This thing is tending to 0. Okay, so we'll look at some of those. That'll be fun. That'll be kind of neato, I guess, maybe, sort of. Yeah, I don't know. Let's see this one here. Oh boy, oh boy, oh boy, oh boy, oh boy. Excuse me. Okay, so this one here looks like, I feel like this is what's happening every time. Well, I don't know. The top stays 1. The bottom is, looks like we're, well, wait now. This feels weird and strange and dirty. I feel like this stayed at 5 and then went to 15 and said, wait a minute. This feels like, it feels like this times 3 gets you 45. 5 times 3 is 15. Wait a minute. What's 5 times 3? It would be 15. Oh, but wait. That would be 3/15. Dude, you freaked us out, man. So I did it on purpose, obviously. So it looks like we're multiplying by 1/3 every time. And what we do when we multiply by 1/3, or if you prefer, or divide by 3, we call this an exponential. Oh, it's exponential. That's true. But we call it a geometric sequence. Okay, and so here's the game. It'll always be given by the first term times what you're multiplying by, which we call the common ratio, to the, in this case, the n minus 1th power. So when you see a geometric, it'll always be a times b to the n minus 1. That's the easiest way to write it. Because when the first term happens, 1 minus 1 is 0. 1/3 of the 0 is 1 times 3/5. Boom, 3/5. When n is 2, 2 minus 1 is 1. 1/3 of the 1 is 1/3 times 3/5 is 1/5. Done. Piece of cake. Okay. Another very common sort of. Oh, I'm going to go back to that for a second. While we're here, I'm just going to milk this one a little bit. If you think about this, could I also write this? Again, this is explicit. or the recursive formula for this would be the first term is 3/5, and then how do you get to the next term? You take 1/3 times the previous term. So whatever the previous term was, you multiply by 1/3. Or if it makes you happy, you could divide it by 3. You could have also written this one as 5 and then 3 to the n minus 1. That would work as well. Okay, that would totally work as well. Just put that on the bottom if that makes you happier. Doesn't make me happy, but if it makes you happier, you knock yourself out, friend. I don't care. I'm just here to help because I care about the children. Okay. Boring. Boring. Well, actually, let's do that one. That's kind of, no, that's boring. Well, that's actually fun. Let's try that. 1, 2, 3, 4, 5, 6. Okay, what's the pattern? Well, G's on top, J. This is the first term, second term, third term, fourth term, fifth term. The top is just n. You're right. Nice work. What's going on the bottom? Well, those are squared numbers. But this isn't 1 squared. This is 2 squared. And this is 3 squared. And this is 4 squared. Wait a minute. This is the third term. Wait, that means the bottom is n minus 1 squared. Ta-da! It's that easy, my friend. That easy. I kind of like these guys. They kind of make me happy, a little happy, anyways. Cool. So then those are sequences. So then what happens if I show it to you in this format? Okay. What if I say to you it is something along the lines of, well, I don't know, 1 plus 4 plus 9 plus 16 plus ... plus 81. Okay. Then all of a sudden it becomes a series, and maybe you've forgotten about that, maybe you didn't know that. A series is a sum of a sequence. Okay? This is what we call expanded form. Okay? We could also write this in what's called sigma notation. Okay? To do that, you would need to have I goes from 1 to whatever n is. Okay? And then in here is where your explicit formula goes for your sequence. So in this case, it looks like it's n squared, yes? So I'm going to take this sum. I goes from 1 to 9 of n squared. This is the same as going 1 plus 4 plus 9 plus 16 plus ... plus 81. They are the same. So sigma notation versus expanded notation. Okay. So we'll do that. Let's try one like, oh, like this guy here, I guess. Sure. What do you think? 1 over 2 factorial plus 1 over, or 2 rather, over 3 factorial plus 3 over 4 factorial plus ... plus. Now wait, what's going on? Well, the top is clearly n. The bottom is, well, this is the first term, but it's 2 for crying out loud. This is the second term, but it's 3. It's n plus 1 factorial. And they show that to you if you look at it. Okay? And so in that situation there, they want me to use the appropriate summation, or so they want me to use summation notation. Summation notation and sigma notation are the same thing. Your book says summation notation, but it's sigma notation is what normal people call it. So it's n over n plus 1 factorial. And it goes from n equals 1 through, I'm sorry, I goes from 1 to n. And that's all we're doing. We're just cleaning it up, making it look prettier. Okay? Remember, n factorial is n times n minus 1 times n minus 2, ... n minus 1, which is 1. And so, for instance, if you want to do 7, it would be 7 times 6 times 5 times 4 times 3 times 2 times 1. If it's anything other than a whole number, it gets ugly and ends in the square root of pi, and it's kind of bizarre, and I don't want to talk about it. So we're only going to give you ones that come out nicely for this portion of it. And there you go. Now, a different kind of sequence can be written like this. This is actually not a summation. This capital pi, where k goes from 1 to n, it's k over k squared plus 4. And they want you to write this in expanded notation, or expanded notation. So when you do this, well, let's think about this for a minute. What would the bottom be? So it'd be 1 over 1/5. If k was 2, you get 2 over 8. What am I doing here? Well, big capital pi means multiply. And then 3 over 13 times ... times k over k squared plus 4. This is a product notation. And so you could take, if you had a long expanded multiplication problem, you could rewrite them like so. Okay. Let's see. Let's do one of those, shall we? So if you have 1 over 4 times 1 over 8 times 1 over 16 times 1 over 32 ... Okay. What would you be multiplying here? Well, I feel like the top is clearly 1. The bottom is clearly 2 to the nth power of some sort. This is 2 squared, that's 2 cubed, so it's 2 to the n plus 1. So I could rewrite this as pi. I goes from 1 to n, you see, of 1 over 2 to the n plus 1. That's all you're doing. Give it one of those so it looks like it's inside of it. That's all. That's it. Nothing to it. Okay? Kind of a fun deal. Almost fun. I don't know if it's totally as fun, but it's not bad. So here's a couple of example ones they want you to work out here real quick. Let's say you had this 6 factorial over 8 factorial. This is just for the ease of computation. It's obviously you can type this in your calculator, and obviously the answer is 56. 1 over 56. However, right, oftentimes it's not helpful in a problem to do this in a calculator, because what you want to do is try to simplify it algebraically. So oftentimes this will come out. What we got here is these guys cancel out. You're left with 1 over 56. Okay. 8 factorial over 8 factorial is, wait for it, 1. That's right. That's right. But it's also, check it out, equal to, get this now, interesting. It's also equal to, 0 factorial. We're going to see in just a minute. Okay. So, later in this book, we already talked about combinations. So combinations of n choose x, or the way your book writes it is nx, like so. Remember, that's n factorial over n minus x factorial times x factorial. Remember, why does it 0 equal this way? Well, think about it. If you had 8 things and you take none of them, how many ways can you do that? Well, you can do it one way. Why is that? It's going to be 8 factorial over 8 factorial times 0 factorial. That gives me 1 over 0 factorial. But clearly there's one way to do it. By definition, then 0 factorial is 1. Okay? I think I mentioned that in our probability lecture, but just making sure we're clear on that. What would happen if you had n plus 1 factorial divided by n minus 2 factorial? Gross, Jay. No, it's really not bad. Check it out. So it's n plus 1 times n minus 1 times n minus 2 times ... Yes? And n minus 2 factorial is n minus 2 times ... These all cancel out. This is your answer. Okay? So that's why I say it's important to understand that and feel very confident with it, because of the fact that it just makes your life that much simpler to fool with. Okay? What if you had this guy, and it wants you to express this as a single summation, or a single sigma notation kind of a problem. So 2 times the sum, k equals 1 to n, of 3k squared plus 4, plus 5, k equals 1 to n, of 2k squared minus 1. And now there's a bunch of different ways. Some people among us would go, Could we just times the 2 inside and get 6x plus 8? Yes. So I'm going to do it about 2 different ways here, 3 or 12 different ways. You'll see what I mean in a second. 6k squared plus 8. Why can I do that? Because this is just a summation. This looks an awful lot like 2 times x plus 5 or something. It's a distributive property. You can bring it in or you could take it out. If I didn't like it in here, I could factor it back out front. This guy is going to be the same of 10k squared minus 5. Since the summations are the same, it's just going to be 16k squared plus 3. And you're done. Okay. Now something else we could have done. We could have just said 2. I'm just going to use the summation only of 3k squared plus 2 sum of 4. Interesting. Plus, I'm going to put k goes from 1 to n on this one here, just for fun. Plus 5 sum k equals 1 to n of 2k squared plus, or minus, sorry. Well, plus, I'll do plus. The sum, 5 times the sum, sorry. K equals 1 to n of negative 1. So let's think about this for a minute. This is kind of a big deal. If I took that out, I can also stick it back in if it makes me happy. So I could make this 6 right here if I wanted to, or I could factor it out front. I get 6 times the sum of the k squareds. Plus, now what is the sum of 4 n times? In reality, this is 2 times 4n, right? And we could leave it like that, or we don't have to leave it like that. Now I'm going to show you this. I could have left it like this, or I could have written it like this, or I could have written it like this. Okay, but either case, it's the same. I think I'm going to go with this route here just for fun. Okay, I'll kind of show you some different things in a second. So I'll pull this out. I'm going to get 10 times the sum of the k squareds plus, or minus rather, 5 sum of the ones. Took the negative with me. Okay. So if you do this, what do you get? Well, in reality, you'd have 8n here minus 5n is 3n, but really we're just going to write it as minus. We're going to get 3 sum like that, and then you got this. It's going to be 6 and 2 is 16, and then of course you can just put the summations back together. Now, whether I care or not, it doesn't make any difference to me. I want you to be happy being able to do it either direction. Sometimes it makes sense to do it one way, sometimes it makes sense to do it the other way. It's really up to you how you go about it. Okay. For instance, if you wanted to find the sum, the actual sum, k equals 1 to 5 of 3k squared minus 2k plus 7. Okay. Well, the guy can do this, break it up. Okay, let's do the hard part first. What is the sum of 1 5 times? It's 5. So that's 35. Cool. Okay. What happens when you add up numbers? Well, it turns out that the sum of k, when k equals 1 to n, is simply going to be equal to k1 plus kn divided by 2 times n. Okay, so in this case it's going to be 1 plus 5 divided by 2 times 5. This is 6 divided by 2 is 3. 3 times 5 is 15. Does that make sense? 1 plus 2 plus 3 plus 4 plus 5. This is 6 plus 4 is 10 plus 5 is 15. Excellent. Oops. That's 15 inside times negative 2. It's negative 30. Cool. And then what is the sum of k squareds? Come on, Jay, you can do it. Can you do it? Can you do it off the top of your head? Or do I have to look it up? I might have to look this one up. Oh, piddle fiddle. It's n times n minus n times n plus 1 times. Let's do it off the top of my head. N plus 1, 2n plus 1 over 6. Is that right? I'll have to look that up. Hang on. Don't move. Don't go anywhere. I'll have to look that up. I wouldn't be in. OMG, Osh. It's like I know what I'm talking about or something. So it would be what? Well, it would be K. So our n is 5 here. So it's 5 times 6 times 11 divided by 6. So the answer should be 55. That makes sense? Well, it's 1 plus 4 plus 9 plus 16 plus 49. Is that right? Did I do that right? Do I do my math right? 2n plus 1 is 11. Plus 1 is 5. So that is 5. 14, that's 30, that's 79. Something's a little screwy there. Come on, Jay. You can do it. Oh, 49, you dumbass, is 25. Okay, let's try it again. So it's 15, 30, 55. Yes. So 165 minus 30 plus 35. Well, that's 200 minus 30 is 170. Ta-da! And so that is where we use that. The idea that the summation passes through is very similar to when you do the derivative, not derivatives, you ding dong. Well, derivatives too, but specifically integrals. Because what are integrals? Integrals are summations. So you can pass the sum through. It's the same principle. Pull the constants out front, things of that nature. Okay, so just hopefully that should not be brand spanking new. It's not terrible at all, anyways. Also want to do one of these guys, maybe two of them. I don't know, whatever. They talk about change a variable. Okay, and so I want to do the sum of I don't know, I times 3i plus 7. And I want to do I equals 0 to 6, I think. 0 to 6. Cool. Anyway, so one in the book gives you something like this. Let's let I go from, or let's let, I guess we'll do this one here. K will equal I plus 1. Okay. So if I were to do this, think about that. Everywhere there's currently going to be an I, or wherever there's going to be an I, I'm going to replace it with a K, right? I want to do this. So I will be equal to K minus 1, right? K minus 1. This is a little algebra, piece of cake, right? It's going to be K minus 1 times, it's going to be 3 K minus 1 plus 7. And then, of course, what is I plus 1 is whatever my K is, right? So I plus 1 will give me what? 1. So K is going to go from 1 to 7. Let's see if that's true. So let's just do this guy and see what happens here, shall we? So if I do this, K equals I plus 1. So let's try this, shall we? So here we're going to have our first term. I'm just going to list my terms out. So 0, obviously. My next term is going to be, well, 1 plus, that's 10, so 10. And my second term is going to be 2. And then 13, which should be 26. And then it's going to be 3. Oh, jeez. Why did I pick such a gross number? 3 times 16 is 48. Disgusting. So this is the 0 term. 1, 2, 3. Oh, there's an easier way to do this. There we go. Cool. So I can just literally do this on my calculator. Alpha I times alpha I times, oops, 3i rather, plus 7. Oh, you hippie. Such that I equals, there we go, 4. 76. and then 5, 110, and then 6. What a pain in the buttocks. 150. Okay, and so if you added those up, 150 plus 110 plus 76 plus 48 plus 26 plus 10 plus 0. Well, that's not hard. Should be 420. And everyone shouts, blaze it at the same time. Great, excellent. So, there we go. Now, I'm going to clean this up a little bit. This is going to be k minus 1 times, it's going to be 3k minus 3 plus 7 is 3k plus 4. Cool, let's see what happens. When you put a 1 into here, what do you get? Well, 1 minus 1 is 0, so you get 0. When you put a 2 in there, you get 2 minus 1, of course, is 1, and then this is 6 plus 4 is 10. Cool. Put a 3 in there, you're going to get 2 times 13, which is 26, and so on and so on and so on. They work the same way. Why on earth would I want to do this? Well, not for this particular problem, but for some problems later on when it's an actual, if you had a situation where, well, this actually would work too. Let's actually FOIL this out a little bit. This would be 3i squared plus 7i, right? Okay. You're like, oh, that's cool. I could use some summation notations. Oh, not so fast, Haas. Because back here, these formulas always start with k equals 1. Ah, crap, I have k equals 0. So there's two ways to do it. Okay, there's two ways to do it. You could use a change of base formula. Okay, a change of index, which is cool, and then you're good to go. So this would be 3k squared plus 4k minus 3k minus 4. K equals 1 to 7. And then this, of course, would be 3 sum k equals 1 to 7 of k squared plus 4 sum k equals 1 to 7 of k minus, oh, not 4, you dummy, it was just 1k, right? Just 4 minus 3 is 1. Minus 4 sum of the 1's, k equals 1 to 7. And the idea is that those formulas I showed you start at 1. They don't start at 0. So what a guy could also do is take the initial one up there, which was 3i squared, and go from k equals 0 to 6. And then what you could do is you could literally just do this and say, well, I need to do the I of 0 term, the 0th term, right, squared times 3, which is, well, you just put it this way. You take the 0th term. I'll just do the 0th term plus the sum k equals 1 to 6, and you can do it this way. You with me? So, for instance, on the first part of that, and then you do the whole rest of the thing, okay? And so the idea would be was what would happen on that first one. What happened when you put 0 squared into this guy right here? Well, if you put 0 into that 0 squared piece, you just get 0, and then you take the next 6 terms, the next 5 terms, and add them together, and you'd get there. It works the same way. It's a little more screwing around. Sometimes I find that easier, though, than doing a change of index. However, so change of index is very important because in almost every math book that comes up at some point. And you're just like, where did they do that? How did they do that? I don't understand how they did that. That's weird. And so just be aware of it. Okay? So that also will come into play on a situation like this guy. The summation that k goes from 1 to m plus 1 of k squared. And you're like, well, what? What? It should go to a single solitary term. I agree. So they actually have you do a few of these guys. Right? And then what is the m plus 1th term? It would be m plus 1 squared. So in other words, you could break off the 0th term and take care of it by itself. Or you could take the m plus 1th term and break it off and deal with it by itself. Both things happen in the sequences and series sorts of things. If you've had Calc 3, of course, that's not new and different to you, probably. You've probably seen that before at some point. Okay? Yeah, that sounds pretty cool, man. Pretty cool. I am going to do one more little thing here while we're here. And that is, in the case of a nice, what we call arithmetic, okay, and if it's a nice arithmetic series like this, so well, let's don't do that first yet. Let's just do this guy here. Nice. Dot, 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 dot. So this is what we call arithmetic. That is, we are adding the same amount each time. You're like, that's linear. It is literally linear. So then it should look like y equals mx plus b. Basically, it does. I think an easier way to write it, though, is to say this. The common difference, in this case, 5 times n minus 1 plus the initial term, t1. So for this case, it would be tn is equal to, we're going to add 5 plus that. So think about it this way. The first term, well, 1 minus 1 is 0, so that's 0 plus 2 is 2. The second term would be 2 minus 1 is 1 times 5 is 5 plus 2 is 7, and so forth and so on. It's very easy. Personally, I prefer just to leave it like that myself. Of course, a guy could do this recursively. One would say this, and one would say that it's the previous term plus 5. Okay? That's for arithmetic. What if I wanted to add them up, you say? Maybe I have a sequence. How would I do that? Cool. Okay. So when you have an arithmetic series, it's always going to be t1 plus tn over 2 times n. Or some people like to write it, and I used to like to do it this way myself. Whatever makes you happier. So for me, it's going to be 2 plus 49, right? Times n over 2. And you're like, well, wait, n over 2, how am I going to find that? Well, remember, this formula that I gave you up here was equal to 5 times n minus 1 plus 2. Well, the term that I'm interested in is number 47, the 47 guy. Minus 2, you get 45 is equal to 5 n minus 1. Divide by 5, you get 9. So n is the 10th term. You see that? So 10 over 2 is 5 times 51 to 55 would be my sum. If it was geometric, these are the only two we have actual values for. If you had 3, 6, 12, 24, dot, 108, you dork. 48, 96, 192, I guess. 192, I think so. Cool, here we go. So this is what we call geometric, because I'm timesing by 2 each time. So explicitly, it would look like 3 times 2 to the n minus 1th power. Recursively, it would be 3, and then the next term would be 2 times the previous term. Okay, to find the sum, one simply does this. You would take t1, 1 minus r to the n over 1 minus r. And no, I'm not going to prove why that is. It is what it is. So it's going to be 3 times 1 minus 2 to the n, I don't know what n is yet, over 1 minus 2. Okay? So let's think about that for a minute. Okay? I need to know what n is. Well, fortunately, I have a formula that will tell me it. If I divide by 3 to both sides, it gives me 60, what, 64? 64, no, 60, oh good heavens, I can't do math. 192 divided by 3. 64. Did I say 64? That just didn't sound right. 64, I don't know. 2 to the n minus 1. How do you solve this? Take the ln of both sides, I guess, is what I would do, right? Unless you're really particularly good at doing stuff in your head. So the ln of 64 divided by the ln of 2 is 6. So n is equal to 7, looks like. So let's plop a 7 in here. And so if I did 3 parentheses 1 minus 2 to the 7 divided by -1, 301 would be the sum of this sequence. Okay. Now, clearly this just continues to blow up to infinity's way over there. So, but what would happen if you had one that looked like this? 10, 5, 2.5, ... forever. Well, we're timesing by a half, or 0.5, if that makes you happier. So it is geometric, faux show, but one has to be careful a little bit here. So what happens is this. The sum is T1, 1 minus r then, over 1 minus r. Now wait, what happens to 0.5 as this goes to infinity? This piece here tends to 0, which means this piece here tends to 1, because it becomes 1 minus 0 in essence. So for an infinite, so for the sum of the infinite terms of this sequence, it would simply be T1 divided by 1 minus r. Or in this case, it'd be 10 divided by a half, which is equal to 20. This one has always mind-boggled me. I'm thinking about this, 15, there's 17 and a half, 18 3/4 in the first 4 terms. That means the rest of the infinity minus 4 terms, which isn't even a thing, only adds up to 1.25, which is crazy, okay? It's an infinite geometric series, we say. We'll spend some more time on that later on, but I just wanted to get that off my chest tonight. So 5.1.